guys' audio if you happen to talk. All it's going to record is just the screen and my microphone. So I can put it on YouTube in case anyone else misses the session. But yes, so this is what we're going to be talking about today. Let's just dive right into it. So Stokes Theorem, remember, we had like the closed surface equation where it was like f dot t ds. And that really isn't too important because what's important is right here, this s, and we've got curl of f, and then we've got dot n dsa. Sorry, someone is talking outside my window. I have to shut my window. All right, there we go. It's also helpful to remember the flux equation. So remember that if we have like f dot n dsa, and I think this is a curve, not a surface. There we go. That's also equal to, if you take the integral across the region, the m fx minus n fy plus p dsa. We did, oh no, it's just dA. We did a lot of these problems on Monday, and it's, if you ever boil down this to this equation right here and you actually have to do out the dot product, it's helpful just to remember that right there. So without further ado, and I'm just going to open up the chat in case anyone has any comments for me. Okay, I've got the chat open. Let's do some problems. So warm up. So use your own notes if you took notes from lecture today, or just try it out for yourself if you're pretty confident with these problems already. See if you can figure out this problem. Find the closed interval of f dot t ds from this surface right here. I will give you guys just a few minutes and we'll see how you guys do. I'll set a timer for, let's say, like 4 minutes. Nice warm-up problem. We'll see how you guys do. Good luck. I believe in you. All right, so we'll see how far you guys got here. So we first started with del cross f, of course, and if you remember how to do the cross product, we just have row x, row over row y, row partial over. I don't know why I call it row. I don't know why I do that. Partial x, partial y, partial z, and then we put in our f equation into underneath there. So it's like 3x minus y, and then 2z, and then 4x minus z. And then once we've got that, we just compute that cross product, and you can watch the Butler's lecture on doing it. But it's -2, -4, and 1. If you guys did that out correctly. And if you do, I applaud you. Next, we need to draw the region and find the normal vector. So you can see I already drew the region here up in the top. And now what we need to do is find the normal vector. It's 1/2 x plus 1/3 y plus 1/2 z is equal to 1 would be the equation of that plane. And we've done a few of those problems, oh man, way back in the day when we had these sessions in person. You remember we just set the right-hand side equal to 1, like 1 is equal to ax plus by plus cz. And then what happens is we just set y and z equal to 0. So then a is equal to, we see that it crosses at x is equal to 2, so a must be 1/2. Stuff like that. So we solved that out. We got that equation. I was actually lost the first time we watched this in lecture too. Next, we need to find like partial f x and partial f y. Well, first we need to find the normal vector. So the normal vector is just going to be, anyone's got it? It would be this, right? So we could say that the normal vector is 1/2, 1/3, and 1/2. And I guess I made a mistake because we don't need to find that. What we need to use is the flux equation. So we could do that out if we wanted to, but instead, using the flux equation, we need to find partial f of x and partial f of y. And we can do that by solving this equation for z. So if you did that, you'd move everything over to the side. So it'd be like 1/2 z is equal to 1 minus 1/2 x minus 1/3 y. And then after that, we get z is equal to 2 minus x minus 2/3 y. So there's our function. So then our f of x is we just take the partial of that with respect to x, which we get -1. And our f of y is equal to, we take the partial of that, -2/3. And now we plug all of that into our equation right here. So now we have double integral. So our -m, so our m comes from, look at the page and think about it really fast where your m might come from. It's going to be this guy. Because remember what we're doing is we're doing, that's our del cross f is like our big F, and then our normal vector dot n is equal to our flux equation. That's what we're using. So we solve for that, so we'll get -m, so it'd be -2 times f of x, which is -1, minus, and then we've got n, which is -4, times f of y, which is -2/3. And then we've got plus our p, which is 1, dA. Got the region. And if we solve all that out, we'll get -11/3 on the outside region dA. And of course, what we're saying right here in that blue box is just find the surface area, or the area of the region, excuse me, not the surface area, the area of the region. So we have to go back into the xy plane and see where the domain of this function exists. Remember, we talked all the way at the start of the semester about domains of three-dimensional functions. So we have to find the domain of that and take the area of that domain. And so the domain on the xy plane is just right here, shaded in the bottom right. And that area is just 1/2 base times height. So it's 1/2 times 2 times 3, which is just 3. So then we would get -11. And that's how we would solve for that. I know it's a little repetitive if you watch lecture, of course, I'm just kind of, but I think it's good to start with something maybe that's familiar before we dig into some of these problems. So are there any questions about that? Anybody have any questions? Awesome. All right, cool. Let's press on. Oh, and I left myself extra space. I thought I was going to run out of space. So this is Fall 19, Problem 8, just identifying steps. So identifying steps, what do you mean by that, Nathan? Nathan says he's just identifying steps.
Just when you look at it and then you're given all the pieces, I think it's just I struggle figuring out where to begin with a lot of the problems because Stokes, Greens, all of it, I swear it all looks the same at the beginning
No, yeah.
and supposed to like decode it, and when there was only one thing it was fine, but now there's like four choices and you're just looking at it wondering what is this? What am I doing?
No, definitely, yeah. So the three dimensions will give it away right away that we might be thinking about Stokes. But we'll look at, I think that's today we'll look at like four different problems, and hopefully you'll kind of just get a familiarity for you see this problem and you'll start thinking Stokes. And then you'll start thinking either Greens or Stokes, and when you start thinking either Greens or Stokes, check if it's 2D or 3D, and we'll press on. I think just practice is the best way to do it. And today, that's what I intend to do. So let's look at this one. This one's from Fall 19. So find the upper hemisphere of that function, upwards pointing normal. So when you see this guy, that's definitely a Stokes problem. That's for sure. I mean, they give that right in the exam. They said del cross f dot n. So you see that and you're like, boom, I know that's a Stokes equation. And then they give you the function to use, which is good. We'll see. I think I'll let you guys run on this. Determine your own. So we'll go through the steps. We'll talk through the steps and I'll let you guys practice. So determine your surface, BYOS, which is like the bring your own surface, if you guys remember Butler talking that, and the normal vector. So I think the easiest surface to use would be that circle. And remember how we determine the normal vector is see these outward pointing arrows we have from our surface. So what we do is just start shrinking that surface inwards. And as the surface keeps shrinking inwards, then all of a sudden it just becomes one arrow pointing straight up. Also, they said upward pointing normal, which is easy. And one last thing you can think of, and this might help you in the last problem we go over in today's session, is right-hand rule actually applies for your normals. So if, and I don't know why they never mentioned that in lecture, but see how we're circling in that counterclockwise motion. So if you right-hand rule that and just curl your hand around that curve, your thumb points straight up, which means your normal is pointing right out of that surface. So our normal is just, remember we talked about in lecture, it's 0, 0, 1 because it has no direction in it, because it's going straight up, it has no direction in the x, no direction in the y, and normal vectors are always unit vectors. So it's pointing just 1 on the way up. So yes. So compute your del dot cross f, and I say look at your normal vector. Which parts do you, and then it got cut off. Oh, that's sad. But it says which parts do you need to actually like need to compute. Because that's important because we just have a 0, 0, 1 here. Remember that once we get to, it'll be del cross f and then it'll be dot n. And our n is just 0, 0, 1. So because we have two zeros, we don't need the first two components of that del cross f. So if we do that, just remember that we've got like I, j, k, and we'll do del over del x, not del, partial of y, partial for partial z. And then what we've got is our f equations right here. I'm just going to put f of x for now, f of y, f of z. And then when you do your cross product, all we want is the y component or the z component. We don't need the x or the y. So to solve for the z, we just want the k. So we don't need anything with the I, we don't need anything with the j, all we want is the k. So find what goes in that k, and then I'll challenge you guys to fill that integral and see if you can solve it. I'll let you guys go, I'll set a timer for like 3 minutes and we'll see how well you guys do. Good luck. All right, let's see how you guys did. So we are looking for the k. So if we do this out, let's think about this. So we'll take our how I do the cross product is that if I'm using h, or if I want to find k, then I just cross that out and cross that out, and I just take the determinant of this guy. Some people do cross products different ways. That's just kind of how I do it. So we'll do the partial x times f of y, and our f of y is xz times j. So if we do that, we'll get partial x times f of y. So we'll get z minus, okay, and now we need to go the other way. We need f of x times partial y, which is f of x times partial y is negative yz times partial y. So we'll get a negative z times k. So we'll get, for our normal vector, or our function vector, we'll get something we don't care, and then something we don't care, and then what we'll get is 2z. And then what we plug into our integral equation, remember we have, I'll do it in another color, keep changing the colors. We have del f cross f and dsa. And if we plug everything in, then we'll get, let's see, we get question mark 2z dot 001 dsa. And now we do that dot product, and hopefully that makes sense. When we do the dot product, we'll get just 2z times dsa. Okay, so if you got here and didn't know where to go next, I don't blame you, and you got pretty far, so that's good. So now we have a z, and we haven't seen any problems before where we actually have a variable when we solve this. So what z do we use? And I'll tell you, it's just right there. We use z is equal to 3 because we're evaluating that closed surface. That closed surface is at the position z is equal to 3. So then we get 6, and then we'll bring it outside the integral r dsa. And now that integral is just finding the area of that inside circle. So now what we need to do is like find the radius of that circle. So we can probably go up to our equation for the circle and figure it out. X squared plus y squared is equal to z minus 3 squared is equal to 9. So if we plug z is equal to 3, we get x squared plus y squared is equal to 9, which is good. It's equal to 9, so that's right there. So that means our radius is equal to 3. So then we'd have 6 times pi times 3 squared, which is just 9 times 6, which is 54 pi. Cool. Cool, not too bad. And that's a final exam problem, which is the second problem we're doing today in our session. So I hope you guys are feeling good about that. Yes, Stokes, are there any questions about that one? Otherwise, we'll just keep getting some practice. So is the area at the end just the region? Yes. So this area, the DSA, is the surface area of like, because I said, remember when we talked about BYOS? So when you choose your BYOS, you pick your surface, and whatever surface you pick, that is your DSA at the end. Your basically your double integral surface area, because it says SA, that's a surface area, and that's like the trick of Stokes is that we use Stokes so we don't have to actually compute any volumes because it's kind of harder to compute. We just use surfaces. 2z to 6. Yeah, of course. So Nathan is asking how we went from 2z to 6. So because our surface is at z is equal to 3, I just plugged in 3 into my z, and then 3 times 2 brought us to 6. And then I just pulled the 6 out. Does that answer your question? Awesome. Cool. All right, cool. Some great questions. Awesome. Any other questions? Oh, yeah. No, yeah. You just plug in the 3. Yeah. All right, cool. Let's see another example. So you get a function equation. If we're taking the exam, I see that del cross f right there, which means that, boom, we're going to be doing a Stokes problem, no question. Upward pointing normals, unit vector. And then s is the surface, x squared plus y squared plus z squared. So if we think back to our days of drawing stuff in 3D, we can draw this region together, which is it's just a big circle, isn't it? It's big, or not circle, big sphere. So it's a big sphere with a radius of 3, but the problem is that it's only above 0. So because z is greater than 0, it's just a big hemisphere um, up on the top. Man, I'm not very good at drawing, but you get the idea. With a radius of 3. So what we have to do is pick our surface, find our normal vector, compute del cross f, and be smart about it. Figure out what we have with our normal vector, and then plug it all into the integral and solve. So I would say our surface is on the inside there. That would be our surface. So our normal vector would equal 0, 0, 1. Because as we shrink that circle in, it's going to be an upward pointing normal. So yeah, all right, cool. So I have our normal vector. I'll let you guys compute del cross f, see if you can get to the integral, see if you can solve it. And yeah, and we'll come back together in, let's say, 4 more minutes, and we'll see how you guys do. Good luck. All right, so let's see how you guys are doing. So we want del cross f, so it'd be we draw out the cross product again to do it. I, j, and k, and then we'd have partial x, partial y, partial z, and then below we would put our function, so it'd be negative 2y, and then 2x, and then xy plus z squared. All right, cool. So remember, we want to be smart about it. The only thing we care about, again, is the k. So we want the k. I just do this, then I do this, and then I want the determinant of that guy. So it'd be k times partial x times 2, so it'd be 2 minus partial y, this would be minus 2. So we get it's 4k. Ooh, 4k. Just like my camera that I wish I had. So it'd be 0, 0, and 4 for our del cross f. Cool. So now that we have that, we plug it into the integral and we solve. So we've got our integral becomes from the Stokes equation. We just plug our Stokes equation integral. It is just the del cross f dot n dsa, and that becomes, so we'll have the del, so it'd be 0, 0, 4 cross, well, it wouldn't be 0, 0, 4, sorry, these are question marks, we don't know what those are, so it'd be question mark 4. We just didn't solve them because we don't need to, because they turn out to be 0 for this equation. 4 dot 0, 0, 1 dsa, and then after we do that, we'll just get 4 dsa. Perfect. Now all we need to know is the surface area of that circle region in there. So we figure out what the circle that, we know the radius is 3. So again, it's just a 4 times the pi times radius squared. So it'll become 936 pi. Sweet. Okay, we're kind of starting to get in a rhythm with these. Let's check out the next one. There we go. Let h be the part of a sphere. X squared plus y squared plus z squared minus 2z is equal to 1, where z is greater than 0. So again, we're above the xy plane. And then f is equal to negative y comma x comma e to the x cubed plus y cubed. And evaluate that surface integral where n are the normal pointing vectors to the sphere which point towards the center. So I think the trickiest part of this problem is drawing a picture and determining the normal vector. That is definitely a tricky part of this problem. So maybe we'll do that part together. So we need to draw a picture, which means we need to know what the shape looks like. So x squared plus y squared plus z squared minus 2z is equal to 1. So if we do z squared minus 2z, that means we're raising the sphere, right? So if we raise the sphere, and we're raising it by, I would guess 2, but you can plug it in, right? You can see where is x squared plus y squared equal to 0, or not, excuse me, but when does that z term cancel out? And it's when your z is equal to 2, because if you plug in 2, it becomes 2 squared minus 2 times 2, so it'd be 4. So we know it cancels out at 2. So we have a sphere like that, kind of, but it stops at the xy plane, remember. So it stops at the xy plane, and at the xy plane, that means it's another little circle. Man, I'm not very good at drawing today. So we got another, oh man, we got another little, another little circle. There we go. That's pretty good. Okay. So we got a little circle on the xy plane, and we need to evaluate the surface integral. I would pick that circle that it crosses the xy plane as our surface. If we have to bring our own surface, I would call that the surface, definitely, where it crosses the xy plane. And so that's the surface. The radius is, you could see what the radius is. If z is equal to 0, then x squared plus y squared is equal to 1. So the radius is equal to 1. That's an easy problem. We still need to determine the normal vector. Obviously, it's either going to be straight up or straight down. Does anybody in the chat have any ideas if it's straight up or straight down? I'll take volunteers. Up, yes. Anyone say down? Nathan says down. All right, let's see. So thank you guys both for guessing. Yes, we've got some chat activity. The normal vectors are pointing towards the sphere. So remember, it looks like this. If they're pointing inwards towards the sphere, it looks like that. And then as we like deflate the sphere, like we talked about in lecture, like we'll start deflating it. They keep pointing inwards and down until it eventually becomes flat. So the normal vector is pointing straight down. So I'm sorry it wasn't down, but or sorry it wasn't up. But thank you for guessing. We had a guess. So the normal vector is going down, which means that if we write it out, I'll see if you guys can do it yourselves. Write it. I'll give you 2 seconds. 1, 2. So it should be 0, 0, -1. Good job, everybody. Yes. So now we have the normal vector. Compute del cross f, and you can be smart about it, definitely. And then solve that integral. And yeah, I'll give you guys another couple minutes. What is it? I'll give you, let's say, 3.5 minutes on this one. And we'll see how you guys do. Good luck. I believe in you. All right, let's see how you guys did. So if you did yeah, that's a good color. We'll do del cross f. If you did del cross f, I'll save the dramatics. You should get you shouldn't care about that first or that second term. All you should care about is that third term, and you should get 2. Because you got the minus y and the x, and they should bring you to positive 2. And next, if we just solve the integral, so we'll plug in the Stokes equation integral f dot n dsa. So if we do that, we will get something 2 dot 0, 0, -1, tricky, DSA. And so we'll get -2 times the integral DSA over our region of our curve that we're caring about. And the surface area is, again, we've seen this a million times now, we're going to get good at these problems. It's just 1, so we'll get -2 times pi times 1 squared, which is just -2 pi. Awesome. Oh, we've got a question. Still confused on how to get the normal vector. Yeah, no problem. So I'll draw a bigger picture so it looks a little better. So like we were talking about in the problem. Oh gosh, the last line. So this is what it looks like. We were talking about. They give us the equation x squared plus y squared minus 2z is equal to 1, and then z has to be greater than 0. So if z is greater than 0, then it's going to be above the xy plane. So we cut it off at the xy plane right there. So we cut it off at the xy plane, and we see a really easy to surface to use for Stokes theorem, because Stokes theorem is all about surfaces. As we have a surface, we can solve this 3D integral with just 2D integral. So we care about this surface right here. And the only thing we need to do Stokes theorem is the normal vector. They say in the problem that the normal vector in this problem points towards the sphere. Yeah, snow globe shape. Yeah. So the normal vector points towards the sphere. So for the surface, the normal vector looks like this. It's all pointing inwards. Because it's a surface that changes, the normal vector is also changing with position. So they don't give us the function of the normal vector. They just say that it's always pointing towards the sphere. And what we can do is kind of like, so we talked about in lecture, like as you deflate, like as the shape changes, as you kind of deflate it, that normal vector keeps pointing inwards. So we get like more and more deflation. It keeps pointing inwards and inwards until we get to that bottom surface, and when we get to that bottom surface, across the whole surface it's just pointing straight down. And then the vector direction, there's no x or y component to that vector direction. It's just pointing downwards. You're just looking for like a unit vector. Does that answer your question? Awesome. Cool. Of course, glad to help. Okay, so we won't have time to finish this problem, but I want to show you that it's always not just in the z direction. You can see that, so there's two things. A, they don't even give us a surface. They just give us a plane, but we can still use Stokes theorem on it. And I know a surface, you might be thinking Green's theorem, but because we have a z in there, we have to use Stokes. But the normal vector is not going to be like a 0, 0, plus or minus 1. Instead, I'll let you think about it. If you have an x, a y, and a z, see if you can think for yourselves what it should be, just for like a minute. And also the sign is important. First, on the picture, we can see that, so it's circulating like, oh, I guess you can't see the motion, never mind, but it's circulating like this. You can kind of see yeah, it's starting to come through. So it's circulating, I guess, I can't really say clockwise or counterclockwise, but in that direction. So if you right-hand rule it, our normal vector is pointing this way. There it is. So our normal vector is pointing that way. So it's positive y. So that means we're not going anywhere in the x, and we're not going anywhere in the z. So it's all going in the y. It's a positive 1. So that would be our normal vector. Then we would compute our del cross f. And we compute our del cross f. Now we don't care about the x, or like the I or the k. All we care about is the j, which if you do it, you'll get -4. And then we just solve it, set it up and solve it. So it'd be this guy right here. It'd be something -4, something dot, and then we'll get 0, 1, 0, and then DSA, and then so it'd be -4 DSA. So then it's just a square. We determine the surface area of a square is just base times height, or just the side squared, which is 1. So then we just get -4 for our final answer, because it's 1 times -4, and we get -4. So yeah, so it's not always in the z, but It could be. This wasn't on an exam. This was I think, a practice exam problem. But yeah, and that is the perfectly timed conclusion of my session that I have. So, yeah, our next session is Sunday at 6:10 p.m. It is Dead Week, I think, if time isn't going crazy. We're going to be still covering a few different topics, but also trying to review. So maybe I'll send out a poll about what you guys want to review most. We'll see. I might send out a Google poll or something, announcements. But yeah. So yeah, 6:10 p.m. I'll see you guys on Sunday. Same link. And yeah, you guys have a great rest of your week. Happy Wednesday. We're halfway there.